So let's talk a little bit about the voltage due to point sources. This is the definition of voltage. Voltage is the potential energy or work done per unit charge on a charge. Okay, so if we've got, let's say this is a positive charge right here. Okay, if we bring another positive charge from infinity, which is, out here somewhere, right? So here's this positive charge. If we bring it in and drag it all the way to some point here, that's some distance r from the center of that thing, we will have had to have done work on that charge to move it to that point. But here's the problem, is that our force is kq over r squared. And as we get closer and closer, that force gets more and more. So there's no simple way to just figure out, okay, what force do we use? Do we use the force here at infinity, which is 0? Do we use the force here at r, which is exactly this, right? And it turns out that this was a problem that puzzled Sir Isaac Newton, so he invented calculus. Okay, now if you do calculus, okay, you're going to get this result here. Okay, what you do is you get this. It's actually very simple. It's more just algebra, right? But you take that that force is kq over r squared. You get an integral, right? And the integral is very simple, and then you have to evaluate it at infinity and at r, and you end up with this, okay? So this is our formula for this, okay? Notice that you can have positive or negative charges, so therefore you can have positive or negative potentials, right? And then this is our, if we're at some position here, okay? And there's our distance r, right? This is the work. By definition, what this means is it's the work per unit charge to take some other charge from infinity to this distance. Okay, now if that's a positive charge, then of course you'd have to do positive work on it to get it there. If it's a negative charge, of course you'd be doing negative work to get it there. It would be at a place of lower potential. It would willingly want to go that way. Okay, so that's our formula. Okay. So let's do an example of this. Here's a Van de Graaff generator. Has an 18 centimeter radius dome, right? So here's this dome. And we are 18 centimeters from the center of a spherical distribution, we'll just assume, right? Okay, so we can use our formula. V is kq over r, and that's the same k we've been using, so it's going to be 8.99 E9 Newton meters squared per Coulomb squared, right? Times 0.83 E minus 6 coulombs. Whoops, get the coulombs in there. That's a parenthesis. Okay, and then divided by just r, not r squared, but just r, so 0.18. Okay, so let's do that. 8.99 E9 times 0.83 E minus 6 divided by 0.18. Okay, and I get that it is positive 41,453. And then there's a lot of 8s. I like that 8 bar, 0.8 bar volts. Now, do our units really end up being volts? Let's see. Coulombs goes away to the bison. And you end up with 1 coulomb there. Meters goes away. You end up with Newton meters per coulomb, which is a joule per coulomb, which is what a volt is, right? That's joules per coulomb. Okay, so the formula seems to have the right units. This is our answer, is 41 kilovolts, right? And then it also, by the way, seems reasonable because it seems like maybe sparks jump through air, and they could jump 4 inches. And it's about 10,000 volts per inch, so this seems reasonable. Okay, that's our formula. Here's 3 more examples after this.